this morning is Maylin Chen, who's joined us this summer from Caltech. Maylin's been working with William over the summer, and today she'll tell us about their project together, enhancing spectroscopic efficiency through automated and modular software infrastructure.
All right, thank you so much, Gwen, for that introduction, and let's get right into it. So we all know spectroscopy is an incredibly powerful tool in astronomy. However, compared to traditional spectroscopy, where you're only capturing one spectrum at a time, multi-object spectroscopy is a lot more efficient, which is really nice because there are a lot of objects in the sky we're interested in. So the additional data we can collect is going to help us improve our statistical analyses, especially for more complex systems. Now, what exactly, why do we need masks? First off, a mask is just something that blocks out some light from reaching the detector on a telescope. And why do we want a mask? It's because there are a lot of objects in the sky in any given area that can be emitting light. If we were to capture all of the spectra from all of these light sources, we would end up with a lot of overlapping spectra on the detector, making it impossible to resolve or determine which spectrum is which. So by blocking out light from all of the objects we're not interested in, we're able to clearly detect the spectra from the objects we are interested in. Now, you can see here, taken to its extreme, you can have a really crowded light field and really efficiently reduce it down to just a handful of spectra. There are a lot of ways to be creating a mask. However, for the scope of this project, we're limiting it to multi-slit spectrographs, which Carnegie has two of, LDSS3 and IMAX. Multi-slit spectrographs use something called a slit mask, which is essentially just a circular sheet of metal with a bunch of rectangular slits cut into them using a laser cutter. And how do you determine where these slits are placed? Well, there's a lot of math and algorithms that go into it, which is why you typically need a piece of software to help you create these masks. This leads us to our current problem where the current software is really clunky to use, making this process into so this process basically requires you to input many specific parameters and use separate terminal commands in order to cut a mask, which makes it really unintuitive for new users to learn and really tedious for experienced users who often want to cut dozens of masks at a time because there is no way to automate the software unless you write your own script, which is really just unacceptable. Moreover, sometimes there are just weird bugs, like the UI missing some text, making the software completely unusable. Moreover, finally, the feedback you get from the mask cutting software is also insufficient. Once you generate a mask, all you get back from the software is an outline of the mask, which means nothing if you can't see the targets you are trying to capture in relation to where the slits are. Additionally, you don't know which objects were included on the mask because sometimes it's simply impossible to include all objects on the mask because their spectra will overlap. However, the software doesn't tell you which objects it excludes. Instead, it returns a massive list of all of your objects, whether or not they were included, with only the use counts to distinguish between the two. So this brings us to the goals for our project. Our first goal is to allow for easier automation of the mask generation process by encapsulating the current software into an API. An API is just a system for two pieces of software to communicate with each other. This should hopefully eliminate the need for users to interact with the current software and reduce this multi-step process down to a few clicks of a button. Our second goal is to update the user interface to a website because websites are a lot more flexible in terms of the display options we can offer, which allows us to add more error checking and user feedback. It's also important to note that I'm working with another intern on this project, Aiden Brandon from PCC, and he will be taking the lead on the website while I'm handling the API. Finally, our goal is to make our software modular and open source so that we can support multiple different spectrographs. Right now, there's a huge variety in terms of the software and quality of that software offered for each institution for their individual spectrograph. However, the overall mask cutting process remains the same regardless of what spectrograph you have. Thus, there's no reason why the same process can't be generalized to include multiple spectrographs. So our goal is, by hopefully spending the time to develop this infrastructure, we can save other developers and other scientists the time it takes to develop this infrastructure, and that they can just take our software, alter it slightly, and use it to improve everybody's lives. And here's a more visual example of what we're aiming for. You can see how nice it is to actually see the mask in relation to the objects you're trying to capture, as well as the clear sidebar that tells you all the information you need to know about the mask, versus just that very unclear outline we saw earlier. Now, what software are we using to make this actually happen? So we're using a lot of frameworks, some of which I'll go into more detail in the next few slides. But essentially for the back end, which is the behind the scenes part of the software, the API, that's going to be written in Django. For the front end, which is the user interface, the part the user actually sees and interacts with the most, that's going to be written in React and TypeScript, two really popular website development libraries. And finally, for software development tools, we're going to be using GitHub, Rough, and Docker. So a bit more about Django. Django is this really popular Python library, but specifically, we chose to use Django REST framework, which is kind of an add-on to Django. And it's really powerful for building REST APIs. And REST APIs are just APIs that you communicate with using HTTP protocol, which websites also use, making it really compatible with our front end, which is, again, a website interface. Moreover, Django has this really unique organizational structure where every project has multiple apps, where apps are just folders of code that are meant for the same, or trying to achieve the same purpose. So thus, by trying to create an app template for a mask cutting API, we can make it so that we have any developer from any institution can take our template, fill in a couple of blanks, put that folder into our project infrastructure, and immediately have a working API tailored to their mask cutting software, making it very flexible in terms of the softwares it can support. So on that diagram to my left, you can think of it as each individual app being a separate API for a separate spectrograph. And all of this is working under one project. Finally, Django is also really helpful in defining databases, which is really nice because there are a lot of parameters that go into the mask cutting process right now, a lot of data, a lot of information that is currently just stored in random files scattered across your computer. However, this centralizes that information and stores it for long-term like historical reference. Next up, we use Docker because it helps us run applications regardless of OS because it's like a mini virtual machine. If you have an M series Mac, you might know the struggle of like running software on it at times, and Docker should hopefully help with that. This is so that scientists can run the mask cutting software locally on their computer because, as we all know, there sometimes isn't internet access at observatories, and so running it locally is an important feature to have. And then next up, we also use GitHub for version control and open source contribution. It allows anyone to get a copy of the code, make whatever changes they want to it, without breaking the entire thing for everyone. Finally, we also use Rough for common code checking for code quality violation. This ensures that the code we write will be understandable for someone other than ourselves and will be maintainable long term. So what did we actually do in this project? Well, we finished the API. It's done. It has all of the functionality of the original software, plus a bit more for quality of life and organizational purposes. However, it's really hard to visualize an API for you guys because it's essentially just a list of functions. So let's move on to something that's a bit easier to visualize. which is the website. As you can see, my colleague Aiden did an amazing job with the interfacing. It looks a lot better than the 2011 software, and it has a very logical workflow working from left to right. And you can see in the middle right there a very big image of the sky that will later on be used to display the mask in relation to the actual objects you're trying to observe. That's still a feature I'm working on right now. Another big change we made was we changed the workflow of the process. So now users start off by creating a project. Projects essentially group masks together if they're meant to observe the same area of the sky. Because again, you're often not just cutting one mask for an observing run. You might be cutting dozens to like test out different configurations, etc. And you don't want those masks like scattered across your dashboard. You want to be able to have like one location. You know, all of your masks are that's related to this specific project. So that helps when you're trying to like find an old mask. Another thing meant for like to help with record keeping purposes is uploading the instrument configuration to the database. So instruments often change, right? Filters break, dispersers are swapped out. So in order for you to like know recreate like the results of a mask, you want to know like the observing conditions under which the mask was performing under. So by keeping a record of what the instrument was like, you make it easier to know exactly what was happening at the time a mask was being used and generated. So once you're done with all of that setup stuff, you move on to uploading your objects to an object list, which is, again, just to help you organize it even more and view it nicely in a table instead of a massive text file. And once you've uploaded your objects to an object list, you're going to be uploading your instrument setup. So it's like, what position is the telescope going to start and end the observing run in? And this is also where the validation check happens. This is when where the observatory can go in and enforce a set of criteria that they want each mask to have, and it also checks if the mask is going to work. If everything is valid, it's going to generate the mask, which is then returned to the user for review. They can review the slit placement, they can review which objects were included. Once they're happy with it, they finalize the mask, which locks it from further changes and lets the technicians know that they can start to convert the mask to machine code, which is readable for the laser cutters so that they can actually cut the mask and install it for an observing run. And here you can see the technician portal I created to help organize the masks for the technicians, as well as keep a complete record of all of the masks that were ever cut. So moving forward, we're planning on adding a lot more features because the infrastructure is so flexible. We have a lot of room to play around with. So there can definitely be a lot more improvements for like quality of life and also just cool features. We're also working with the Caltech Optical Observatory software group to integrate the LRIS-2 spectrograph into our software, which will provide a lot of helpful feedback regarding like the app template I mentioned. Finally, we're going to be working on deploying this to the cloud so that you guys can actually access it and use it yourselves. Thank you. Do you guys have any questions?
Great questions for Maylin.
This is such a cool project.
Thank you.
I had a question about the website that you're making. Is it a website that's online and when people upload all their information to it, it gets saved somewhere else, or does it get saved locally on their machine? They could access it, or do you have another database that you're saving all their information in? Vector account of some sort.
So it's very flexible in terms of like what the data storage options are. If you're going through the website, it's going to be stored on a database likely hosted on like Amazon Web Services. However, there's also an option to like download your configurations from the website so that you can store a copy of it locally if you want. And if you're running it locally on using like a Docker container for say, then it would be stored on your computer locally.
Other questions?
Thank you. This is a great talk and something that's been desperately needed for a while. Have you been able to cut any masks yet?
We're able to like, yeah, so from the API, we're able to like go through the entire mask cutting process. So that completely replaces the old API. The website we're still finishing up with some features like visualizing the slit and stuff like, slit mask and stuff like that. But aside from that, it should be finished very soon, yeah.
One more question.
You mentioned that you can connect this framework to databases. So I was wondering in particular, will there be a database for standard stars that it also can account for like the proper motions of any given day? So when you're cutting the method, like actually taking the other best guess of where the stars are at the time of observing.
Unfortunately, I don't think we quite got to that stage of like the development process. We were mainly focused on recreating like the main pipeline of the mask cutting software, and we were basically just encapsulating all of its like the old software's functionalities. So we didn't actually work that much with regards to like the actual like algorithms, um, the science that is needed to like help with the mask cutting process. We mainly worked on making that process a lot more usable and understandable.
All right, let's thank